Let's now see how to incorporate the facility of interrupt driven IO into our simple computer. So assume that you are executing the program. Now what I wanted to do is, I'll not write the program in such a way that our program will wait in a loop until some IO happens. So what we'll do is, we'll be executing some other instructions in a program, and whenever there is an interrupt, I'll execute the interrupt that IO related instructions. So assume that we are running a program. Okay, this is a user program, and we are now at instruction number 200. If we are running the instruction number 200, what will the program counter contain? If you are presently executing this, then definitely program counter will contain the number 201, isn't it? It means that the next instruction that has to be executed is 201. Right? Assume that at this point there is a IO request. IO request means, I hope you remember that there are two flags. One is FGI, which indicates that this is a flag, and in case if this flag happens to be 1, it indicates that there is an input from the input IO device present in our register, and you are supposed to read it. And FGO, output flag, if this is 1, it indicates that whatever output you have sent into the output register is already being read by the output device, and you can write a new word. So whatever it is, whenever these two flags, either this one or this one is 1, either this one is 1 or this one is 1, then it means that you are supposed to execute the IO related instructions. Got it? Now at this point, assume that something has happened, either FGI equal to 1 or FGO equal to 1, something has happened. Then what we are supposed to do, that is all let's discuss now. So I don't want to write a loop. I'll write somewhere, let us say this is memory number 2000. In this I'm going to write a program, and that program, the main feature of that program is, it will check which one of these two have happened. Either both of them has happened or one of them has happened. Which one of these two has happened? So in case if input flag is 1, then it will take the corresponding action. So what is the corresponding action? Read the input byte into accumulator and then transfer it to memory or whatever it wants to do. Similarly, if this one has happened, then it will transfer the word which is present in the data register or accumulator into the output register. So depending on what has happened, we are going to handle that action here, right? Let us say it is at 2000. So at this address starting 2000, I have written a program, and let me call this program as the interrupt service routine. In this case, what is causing the interrupt? Only way we will get the interrupt is when there is a IO activity. Got it? So that is why it is called as interrupt driven IO. Now how to incorporate all this? So now see this, whenever you are getting an interrupt request here, which means if one of them is getting 1, whenever you are getting the interrupt request here, you are automatically supposed to go there, execute it completely, and then come back here, right? Therefore, if you have to come back to this location, definitely you are supposed to save this address somewhere. And what are the various options we have? One option is, you can save this address in one of the CPU register, or you can save this address in a memory stack, or you can save this address at a fixed location in the memory. So which one is the best option in case if you are looking at nested programs or nested subroutines or recursive calling? Then obviously memory stack is the best one. But in our small computer, I don't want to complicate the things. That is why I'll use the simplest method. So this particular return address, I'll try to store it at some fixed location in the memory. And just to keep the thing simple, that fixed location, I'll choose it as location 0. So this particular return address 201, I'm going to store it at a fixed location which is 201. Sorry, fixed location is memory address 0, and at memory address 0 I am going to store it. okay, and also I should remember where I have placed this interrupt service routine, right? For that reason, let us say this is 2000, right? Therefore I have to somehow, after storing this particular memory address there, I have to go to the address 2000. That is why below that, at location 1, I'll place a unconditional branch unconditionally to address 2000. Got it? Now what happens is, whenever I see that there is a request, IO request, then I'll automatically go and save the written address at this point. In case if the IO request has happened at 200, in case if the IO request has happened at 300, then I'll be storing 301 there, isn't it? Then the next after storing it, I'll directly jump into the interrupt routine and I'll execute the interrupt routine, and after executing the interrupt routine, I'm supposed to go back, right? Go back to this particular address. For that reason, I'm going to write unconditional branch again. Now what should I put there? Can I put unconditional branch 201 here? I cannot put 201. The reason is simple. If I put 201 here, what happens is, wherever the interrupt occurs, after the interrupt is being serviced, you'll always try to go into that 201 here. So I cannot write 201 there. Instead of that, I'm going to write unconditional branch to 0, right? But then what does it mean? If you go to the 0 address, it is not an instruction to execute. So how does it make sense? It will make sense only if 0, this particular instruction, is using indirect addressing mode, which means you are going to unconditionally branch to some address and that particular address is present indirectly at this address 0. Got it? Then it is called as indirect. So try to understand this one. Simple. What I mean to say is, I have already stored some address here. Now I am giving indirect addressing here. So by this I mean to say that you go to address number 0 and there whatever address is present, you branch to that particular address. Therefore our program can come here and it can automatically resume, right? And what will this IO service routine will do? It will check what type of IO it is, whether it is input or output, and it will execute the corresponding instructions to take the action, and the action which you wanted to do, you are going to put there. So nowhere there is going to be any loop, because we are not actually waiting for this flags to go to 1, right? Flags to set. We are normally executing our program, and whenever these flags happen to be 1, then we are going to perform this. Therefore there is no waiting at all. So busy waiting is completely eliminated. Got it? So now how to make all this happen? Of course we are going to build the hardware. How should the hardware be framed in such a way that all these things should happen? So for that reason we have to develop the hardware, right? Now what are the various flags we have seen? One is FGI, FGO. These will indicate input and output, and along with that we have IEN, interrupt enable. So this flag will show or say whether you are going to allow the interrupts or not. When you are executing a user program like this, right, you are supposed to allow the interrupts. So whenever you are in user mode executing this, then this IEN will be 1, and whenever you are from here you are trying to execute this interrupt service routine, when you are executing the interrupt, generally in most of the cases we follow this. Whenever you are servicing one interrupt, we don't want to get another interrupt. So for that reason, whenever you go from user mode to the super user mode, or whenever you are going from the user program to the interrupt service routine, then you are supposed to make it to 0. So we are going to use this flag as well. Got it? So using these 3 flags, I am supposed to know whether I should raise an interrupt or not. Got it? So for that reason, I am going to use a new flag which is going to be let's call it as R. Okay, now this R flag indicates that there is an interrupt. Now how to set it? So how to set this flag is, I am going to use an AND gate like this. So what is the condition that you should raise an interrupt? So whenever there is an interrupt, first of all, if the interrupt has to be raised, then you should enable the interrupts, and then any one of these two gates should be 1. Therefore, one of these gates should be saying 1 and this one should definitely be 1. Then only I want to raise the interrupts. So see this, how am I going to design this? One is going to be IEN, right? And the other input is going to come from this OR gate. And this OR gate is going to be given these two flags. One is FGI and FGO. Now check this. So whenever IEN is 1, then if any one of these two is 1 or both of them are 1, then we are going to get a 1 here, right? So whenever we get 1, what does it mean? Our program wants to be interrupted. If our program doesn't want to be interrupted, then this particular IEN will be 0, then we will never be getting any interrupt there. Whenever this one is 1, it means that our program wants to be interrupted, and then one of the input or output conditions is 1, which means you have to service either some input or output. That is the meaning of it. Got it? So what happens is, let us say you are actually executing some instruction. You have performed T0, T1, which are fetch, and then T2, which is decode, and then from T3 either you are computing the effective address or you are executing. You are doing something, right? You are done, and once it is done, again you are going to get T0, right? So whenever you get T0, I want you to check this particular flag, right? And if this particular flag is set, I want you to perform these actions. What are the actions? You have to store this particular program counter in this location, right? And then load the program counter or with the next location, which means 1, and you start executing from this instruction. Once you start execution from this instruction, automatically your program control will go there and everything will be done. Got it? These are the actions I want you to do. Now whenever R is 1, are you understanding it? Earlier we didn't consider this R. Whenever it was T0, we are directly getting, earlier whenever it is T0, we are directly getting into the instruction cycle and we are starting the fetch. Now I want to distinguish between two cases. Whenever R is 1, it means that there is an interrupt and you have to get into the interrupt cycle. Whenever this one is 0, it means that there is no interrupt and you can continue with the instruction cycle. Therefore, either you are going to do the interrupt cycle or the instruction cycle, depends on what the value of R is, right? So now that is why I am going to add these two. If the condition is this, if it is R and T0, if the condition is this, then I want to perform. What does it mean? You have just finished executing some instruction, let us say 200 in this case, and after executing that instruction you have found out that R is 1 and T0 is 1, which means whether there is an interrupt, and now you are supposed to perform the interrupt cycle. So let's call it as interrupt cycle. So interrupt cycle will start with R T0. Now what are the actions that you want to perform? So one action that I want to do is, whatever is present in the program counter, I want to store it in the memory at location 0, right? For that reason I have to initialize AR. What is AR? Address register. So address register has to point to 0. It is nothing but clearing the address register, right? So whenever I give the clear to any register, that clear will get executed at the end of the clock cycle. That is why in this entire clock I cannot do any other operation, because I want this one to be done first, okay? And then in the next timing signal T1, what I can do is, in the memory which is pointed by AR, which means that particular location, I want to send program counter. Got it? And after that, this program counter, I want to clear it, and after that I want to increment it. So this one will be done by giving the clear, and this one will be done by giving the increment. I cannot combine these two because clear will happen at the end of the clock, as well as increment will also happen at the end of the clock. If I combine them both, they will not work together. That is why I am using this. So it is going to take 4 clocks, isn't it? In order to cut it short, maybe I'll try to perform some few things so that it can be cut short. See, now when program counter's value is being transmitted into the memory, can I clear the program counter? I cannot do that, because it might so happen that the value that will be sent to the memory will be 0. That is the reason what I'll do is, at this point I'll use the temporary register. I hope you remember that there is a temporary register in our registers, right? So whatever value is present in program counter, I am going to store it in temporary register, because in this clock bus is completely idle, because we are using the clear input to AR and it does not require any bus. So since the bus is completely idle, I am using the bus to transfer the program counter value into the temporary register. Got it? Now since temporary register now contains the value 201, which was earlier present in program counter, I'll use the temporary register to go there, and I no longer require program counter in this clock. Therefore, in this clock itself, I'll clear program counter. So bus is containing the value TR, and for clearing the program counter, I don't need the bus, right? And so I can cut short this process by 1 cycle, right? I can increment this. Program counter is incremented by 1. Are you getting this? Okay. Now along with this, I am supposed to perform few things. Now if you observe it, what we are trying to do is, from here, once I put program counter equal to 1, automatically it will jump to this particular address and it will start executing this, right? So at this point, I don't want anyone to interrupt our program, right? So whenever one interrupt is being handled, I don't want one more interrupt to interrupt this interrupt. Got it? So for that reason I have to write something here. I have to disable the interrupts. So for that reason I am going to set IEN to 0. I want to disrupt this, and also or interrupt flag to 0, right? And also SC to 0. Why SC to 0? Because from T2 I don't want to go to T3, I want to go to T0 again. So next time when T0 happens, R is of course 0, therefore I have to couple with R prime. So whenever there is R prime T0, now try to understand this one. Whenever there is R T0 is true, it means that there is an interrupt and you are starting after an instruction execution. Therefore you have to start with the interrupt cycle. In case if R is 0 and if it is T0, it means that it is not an interrupt. You are supposed to start with the normal fetching of the instruction. So in this case it is fetch, right? T1, these two are fetch, and R prime T2 is decode. So in all our earlier, whatever we have discussed till now, in all our earlier discussions, whenever I said T0, T1, T2, you are supposed to couple with R prime, R prime, R prime. So these two conditions are important. If the clocks are T0, T1, T2, then depending on the value of R, it is either going to be present in the instruction cycle, isn't it? This is instruction cycle, or it is going to be present in interrupt cycle, right? So interrupt cycle is going to end at T2, and after that it is going to generate T0, right? But here it need not end at T0, and next one is T3. So when you are at T3, you need not check whether it is R or R not, or whether R is 0 or 1, because it is already over. The interrupt has already been processed. So T0, this entire thing is generally execute. Are you understanding this one? So what we did is simple. Whenever you are executing a program, whenever you get an interrupt, then you are supposed to service it. So how can we service it is, we are not going to do anything until we execute the present instruction. So whenever you are executing the present instruction, which means if you are in T3, T4 or something, whatever, whenever you are executing, you will not do anything. but then after you finish the execution, whenever T0 is generated, then we check for OR, whether OR is 0 or OR is 1. If OR is 1, then it means that there is an interrupt and I have to service it. So for that reason, in order to service it, I am going to store the return address into this. So one more thing, what are the various things that we are supposed to save in case of interrupt? Along with this particular return address, we are also supposed to save the context. Context is nothing but all the registers of the process along with the flags. But then in this case, our interrupt service routine will not be using any of the registers, or it will not be changing the values present in the registers, because I am going to write the program in a simple way, in such a way that it will just check what type of interrupt it is, and it will either give the INP or OUT. Only these two instructions, and these two instructions are not going to change the contents of any registers normally. In case if you think that our interrupt service routine is going to change the contents of the registers, then in this case, so during this interrupt cycle you are supposed to save all the register contents also, but I want to keep the thing simple, therefore we are not going to do that. In general it has to be done. Okay, so we are going to save the return address there and then service this and again come back. Now one thing you have to observe here is, before I leave the control to the interrupt service routine, I am actually disabling the interrupts, right? Therefore after coming back from here to here, you will not be seeing at the interrupts at all. Once this one is made 0, once IN is made 0, OR will always be 0, which means from here there is a danger that you will never be able to see the interrupts. Even if there is a request for IO, your interrupt flag will never show 1. Got it? So since you have made this one as 0, you are supposed to turn on the interrupt, or you are supposed to enable the interrupt by using ION. So last but one instruction here, somewhere in this has to be ION. By putting this instruction, automatic, earlier if this one was 0, now this one will be changed to 1. Got it? So what are the other things that you should be checking here is, there is one important thing. Assume that now the clock cycle is 0 and you didn't see that there is an interrupt, which means the condition that will be hit is R prime T0. So what will this trigger? It will trigger the fetch cycle. So now you are doing this particular fetch cycle of the fetch phase of the instruction cycle, right? And suddenly during this whenever this one is happening, something has happened from the input device, and then this one is being set. There is a request for input. Then what happens? All of a sudden, even though earlier it was not 0, it was not 1, now it will suddenly become 1, which means when you have executed this one, when you are executing the fetch phase of the instruction cycle, suddenly when you go to T1, it will be R1 T1, which means this one will suddenly become 1 and this one will trigger, which means there is a chance that when you are during the execution of an instruction, you might jump from one phase of the instruction without completing the instruction into the interrupt cycle. So just to stop that from happening, the condition for this one, one more condition is added, that is this particular R1 has to be set only after T0, T1 and T2. Only after you perform T0, T1 and T2, then only you are supposed to set it. So even if you get the IO request at any of these phases, you are not supposed to change the value of R, because there is a chance that you might jump from instruction cycle to the interrupt cycle. For that reason, to this AND gate I'll apply even these clocks also. So I want to see that this should not happen during these 3 cycles, right? So what I'll try to do is, in case if it is not T0, not T1 not T2, then only I am going to set this. Are you getting this? In case if it is T1, then what happens is, if it is T1, this one is going to be 0, right? So is it right? So how should I write it? See, what is that I wanted to do is, I want to give the input like this. I think that is not right. So what I wanted to perform is, if it is not T0, if it is not T1, if it is not T2, then only if I have enabled the input, this interrupt, which means IEN, and either if input flag or output flag is 1, FGI or FGOut is 1, then only I want to set this OR. In this condition only OR has to be made to 1. This is what I want to happen, right? I want this one to happen. Then what is that I should give here is one more AND gate, I guess. Yes, to the AND gate I have to give these three inputs. One is T0 prime, T1 prime and T2 prime, and this one will be given to this. Okay, so I hope you are understanding this. So whenever you are in T0, T1, T2, I don't want OR to go directly from 0 to 1, right? So if the OR was earlier 0, if it suddenly jumps to 1, then what happens is, from your instruction cycle, without finishing the instruction, there is a chance that you might jump to the interrupt cycle. Now by writing like this, I have taken care in such a way that once you have started fetching an instruction, until you finish it, you will not get to interrupt cycle. The reason is, only way you can interrupt into the interrupt cycle is when these three conditions are on. In fact, when this condition is on, and this condition will be on only when you get T0, and you will get T0 only after executing an instruction. And just to stop you from entering into the interrupt cycle from anywhere in T1 or T2, I am not going to make OR as 1. Are you getting this? See, whenever T0 is 1, then I will check whether to get into this one or this one, right? And whenever T1 is 1, I'll make sure that in case if OR is not 1 in T0, then OR will not be 1 in T1 or this, which means whenever you start an instruction execution, you are definitely supposed to finish the execution completely, fetch it, decode it, execute it and completely finish it. Then only at this point, when you get T0, you have to check whether to start the next instruction or the interrupt. Once you decide that you have to start the interrupt, then your interrupt cycle will start here, right? T0, T1, T2, and after that you will start with the next instruction. So in case if you have finished this interrupt cycle, the next instruction will be fetched from here and automatically it will continue on, right? So till this point on, no one can interrupt you again, right? After that you can come back and execute it. Okay, understood this? So anyway, even this one is also not very efficient. The reason is simple. We are actually, whenever there is an interrupt, we are actually wasting this entire thing, right? This is called as overhead, because you have to do all this, isn't it? So if you observe it, it is far better compared to the programmed IO, because in programmed IO we have seen that in order to just transfer one character, we are wasting a lot of instructions, nearly 10 power 5 instructions we are wasting. We are not doing anything. But here we are not wasting those many instructions. In fact, if you are looking at these three clocks, T0, T1 and T2, they are smaller than one instruction. Therefore, you might waste one instruction and then few instructions here, but they will not be, these many, isn't it? 10 power 5 is nothing but 1 lakh instructions. They will not be 1 lakh instructions, but they will be less number of instructions, maybe 100, not even 100 instructions, maybe some 20-30 instructions you will have. So from here you are just wasting very less number of instructions, right? But in case if you have to store the entire context of the processor, then you might waste more instructions. But anyway, the wastage is far less compared to IO, programmed IO. So programmed IO is wasting a lot of instructions compared to our interrupt driven IO. Now there is one more alternative which is not possible in our computer, but then in most of the present computers, if you have very good hardware, sophisticated hardware, there is one more type of I/O possible, that is called as DMA, direct memory access. This particular part we shall see later, because in our computer anyway it is not possible, that is why I am not teaching here, but later we shall again see it. So what is DMA is, I'll just give you a small hint here, later we shall discuss in detail what it means. So DMA is simple here, see this. Till now we are seeing that CPU is there and I/O is connected to this and then memory is connected to this. So only way the movement is happening is through this one, right? What if our common bus is here and CPU is connected to this and then I/O is connected to this and then memory is connected to this? In this case your I/O devices can directly access the memory, that is called as direct memory access. But in our computer it is not possible because the hardware is designed, or the hardware has already been set up in such a way that every transfer is through CPU. But in case if you have such facility, then you can make use of a special capacity called as DMA, direct memory access. In this case CPU need not be involved in I/O transfer except in the beginning and in the ending. That is far more efficient compared to interrupt. Got it? So in order to do I/O, there is programmed I/O, there is interrupt driven I/O, and then there is DMA, right? So we shall see DMA soon after we discuss about the I/O processors and then DMA controllers. So I/O channel and what are the types of communication. So there are something to be discussed before we discuss here. Okay, so whatever it is, we have discussed about all the types of instructions that can be performed and how to perform those instructions in our simple case of computer. Now if you want all this to happen, you are supposed to generate the control signals, isn't it? How the control signals are generated, we shall see it now. Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is, we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.